Imagine you're getting ready for school. You want to find the fastest way to get there. There isn't just one road from your home to your school. There are many different streets you can take. Some streets are short, but they might have a lot of traffic lights. Other streets are longer, but you can drive faster on them. So how do you figure out the absolute best route? You need a way to compare all the possible paths. You have to consider the time it takes to travel down each street. This is a classic problem of finding the shortest path, and it's something we solve in our heads almost every day without even realizing it. This daily challenge is not just about getting to school. It happens when you plan a road trip with your family. You want to find the quickest route to your vacation spot. It also happens when a delivery driver needs to bring a package to your house. They need to find the most efficient path to save time and fuel. In all these situations, you have a starting point, like your home, and an ending point, like the school or a vacation destination. Between these points, there are many connections or roads, each with a cost. The cost could be the time it takes, the distance in miles, or even the amount of traffic you might face. To solve this, you could try every single possible path. You could write down every route and add up the time for each one. But this would take a very long time, especially if there are many streets and intersections. If you have a city with hundreds of roads, the number of possible paths can become enormous. It would be almost impossible for a person to check them all manually. This is where we need a smarter method. We need a systematic way to explore the options without getting lost or checking the same path over and over again. We need an algorithm, which is just a set of rules to follow to solve a problem. This is exactly the kind of puzzle that computer scientists love to solve. They have developed clever methods to find the shortest path in a network of points and connections. This network is what we call a graph in mathematics and computer science. The places like your home and school are the nodes or vertices. The streets that connect them are the edges. Each edge has a weight, which represents the cost, like the travel time. The goal is to find the path from the starting node to all other nodes with the minimum total weight. One of the most famous and useful algorithms for this is Dijkstra's algorithm. So what exactly is this powerful tool called Dijkstra's algorithm? Think of it as a recipe for finding the shortest path. It was created by a computer scientist named Edgar W. Dijkstra back in 1956. His goal was to create a clear and efficient method to find the shortest way from one point to all other points in a network. The algorithm is incredibly reliable. It guarantees that it will find the best possible path as long as none of the path lengths or weights are negative. You can't have a road that takes negative 5 minutes to travel, so for problems like finding directions, this works perfectly. The main idea behind Dijkstra's algorithm is to be greedy, but in a smart way. It always focuses on the path that looks best at the moment. It starts at your beginning point, let's say your home. It then carefully explores the network, one step at a time. The algorithm keeps track of the shortest distance it has found so far from your home to every other intersection or node. At first, it doesn't know any paths, so it assumes the distance to every place is infinite, except for your home, which has a distance of 0 from itself. It then systematically updates these distances as it discovers shorter and shorter routes. Let's use our map example to understand this better. You start at home. The algorithm first looks at all the intersections directly connected to your house. It calculates the time to get to each of these immediate neighbors. Let's say it takes 5 minutes to get to intersection A and 10 minutes to get to intersection B. The algorithm notes these down. It then picks the closest intersection it has found so far, which is intersection A. It's greedy because it chooses the shortest and most promising option available at that moment. It then explores the paths leading out from intersection A to see if it can find even shorter routes to other places. This process is very organized. The algorithm maintains 2 sets of nodes. One set contains the nodes that it has already visited. A node is considered visited once the algorithm is certain it has found the absolute shortest path to it. The other set contains the nodes that it has not yet visited. The algorithm repeatedly picks the unvisited node with the smallest known distance from the start. It then visits this node and updates the distances to its neighbors if a shorter path is found through this newly visited node. This continues until all reachable nodes have been visited, ensuring every path is considered methodically. Let's walk through a simple example to see Dijkstra's algorithm in action. Imagine a small map with 4 locations: home, a library, a park, and school. We want to find the shortest path from home to all other locations. First, we need a table to keep track of the shortest known distance to each location and the previous location on that path. Initially, the distance to home is 0. The distances to the library, park, and school are all set to infinity because we haven't found a path to them yet. We also have a list of unvisited locations, which starts with all 4: home, library, park, and school. Now we begin. The first step is to select the unvisited location with the smallest known distance. Right now, that's home, with a distance of 0. We mark home as visited. Next, we look at its direct neighbors. Let's say the path from home to the library takes 10 minutes and the path from home to the park takes 15 minutes. We update our table. The distance to the library is now 10 via home and the distance to the park is now 15 via home. The distance to school is still infinity because it's not directly connected to home. Our unvisited list now contains the library, park, and school. We repeat the process. We pick the unvisited location with the smallest known distance. Looking at our table, the library has a distance of 10 and the park has a distance of 15. The smallest is 10, so we select the library. We now mark the library as visited. From the library, let's say there's a path to the park that takes 4 minutes and a path to the school that takes 20 minutes. We now check if we can find shorter paths through the library. Let's update our distances. To get to the park, our old path was directly from home, which took 15 minutes. The new path through the library is home to library to park. The time for this path is 10 to the library plus 4 to the park, which is 14 minutes. Since 14 is less than 15, we found a better route. We update the distance to the park to 14 via the library. To get to the school, the path through the library takes 10 plus 20, which is 30 minutes. Since the old distance was infinity, 30 is better. So the distance to school is now 30 via the library. We keep repeating this until all locations are visited, and our table will hold the shortest paths. To summarize, Dijkstra's algorithm follows a few key steps over and over. First, you set the distance to your starting point to 0 and all other points to infinity. Second, you mark all nodes as unvisited. Then, as long as there are unvisited nodes, you select the one with the smallest known distance and mark it as visited. For this current node, you consider all of its unvisited neighbors. For each neighbor, you calculate the distance of the path through the current node. If this new path is shorter than the previously known one, you update the distance. You repeat this until every node in your network has been visited. The beautiful thing about this algorithm is its efficiency and its reliability. It doesn't just randomly guess or check every single path, which would be very slow. Instead, it builds upon what it already knows, always expanding from the most promising point. By the time the algorithm finishes, it has constructed a complete map of the shortest routes from your starting point to everywhere else. This makes it a fundamental building block in computer science and network theory. It provides a clear step-by-step process that a computer can follow very quickly, even for very large and complex networks with thousands or even millions of nodes and edges. The real-world applications of Dijkstra's algorithm are all around us. Every time you use a GPS app on your phone, like Google Maps or Waze, to find the fastest route to a destination, you are likely using a version of this algorithm. It is what allows the app to calculate the best path in seconds, considering things like distance and current traffic conditions. It's also used in computer networking. When you send an email or visit a website, data is sent in small packets over the internet. Routers use algorithms like Dijkstra's to find the best path for these packets to travel across the complex network of the internet to reach their destination quickly. Beyond just maps and the internet, its principles are used in many other fields. It can be used in airline scheduling to find the cheapest flight routes. It can be used in logistics and supply chain management to optimize delivery networks. It can even be used in more abstract problems, like in social networks, to find the closest connection between two people. By understanding Dijkstra's algorithm, you are not just learning a clever puzzle-solving technique. You are learning about one of the core ideas that helps power our modern, interconnected world and makes many of the services we rely on.